Unit 7, Financial Math. Video Lesson 6, Amount of an Ordinary Annuity. So up until now, the questions that we've done involve a person putting in a specific amount of money, depositing it, and leaving it there for a certain amount of time, and then the money accumulates to a certain amount. So they only ever deposit money once and then just leave it. An annuity is a little bit different because it involves a series of equal payments or withdrawals at equal time intervals. So this could mean that you're putting in, you're making payments or putting in a deposit every month, every day, every 6 months, every year. As long as there are payments that are being made, it is called an annuity. If payments, withdrawals are made at the end of each time interval, then the annuity is simply called an ordinary annuity. Some examples of ordinary annuities are mortgages, car loans, and retirement savings plans. Whoa, just lost my screen. Okay, here we go. So these are all examples of times when you make payments or withdrawals at the end of the month. All right, let's take a look at an example. Rohit is saving money from his part-time job. He deposits $200 at the end of every month into a savings account, which pays 2.5% per annum compounded monthly. How much money will Rohit have after accumulated at the end of 1 year? And I realize I just lost my pens, so I'll just grab one from here. All right, so his regular deposits are $200 and his interest rate is 2.5% compounded monthly, and we want to know how much money he has at the end of 1 year. Since we're doing 12 payments of $200, we need to treat each payment as a principal and determine the accumulated amount of each payment. Since they're in the account for different time periods, they will all have a different number of compounding periods. So essentially, we're treating every single $200 deposit as a separate compound interest question. So take a look at the table. It should hopefully make things clearer. So his first payment that goes in is of $200 at the end of the first month. That means that there's 11 months left during that year. So that first payment of $200 is going to remain in there for an additional 11 months accumulating money. So we can use the compound interest formula, and I'll see how I did the 2.5 divided by 12 because it was compounded monthly. And this A will tell us how much money the $200 earns him after the year. Then payment number 2, that's at the end of the second month. So this payment of $200 or this deposit of $200 will only be in the account for 10 months. So I can calculate how much money that $200 will make after 10 months. And then the third payment of $200, it's only in there for 9 months, etc. So if you just keep making monthly payments all the way down, eventually we get down here. At the end of the 12th month, you don't deposit anything, so that money's not going to make you anything. But the 11th payment, that's only in there for 1 month. So this last part here is going to tell you how much money you got on that last $200. So you can treat it as being 12 separate compound interest questions. If you actually calculate each of those, so this is the first one, this is the second one, third month, fourth month, etc., all the way to the 12th, and you add them up, that's how much Rohit will have at the end of 1 year. Don't worry, you don't have to make a table like this every single time. This is way too much work. There is a formula, though, that you can use to get that answer in one step, and this is the formula right here. So A equals R times 1 plus I to the n minus 1 all over I. So you want to calculate what's in the bracket and then multiply by R. Well, let's take a look what the variables mean. A is still accumulated amount, just like in compound interest. Sometimes this formula is written as being equal to FV, which stands for future value, similar to what you've seen on the Inspire. R is the regular payment. I is the same as compound interest, so it's the rate divided by the compounding period, and N is still the same thing. It's the number of, it's number of payments, which is always equivalent to the number of times you get interest. The reason why that is because you have to make sure when you're using this formula that the compounding frequency matches the payment frequency. All that means is if something is being compounded monthly, the payments have to be monthly. If something is being compounded daily, the payments have to be daily. So those have to match. And because those match, then N, which is number of payments, will also be equal to the number of times you get interest. So it's the same calculation, you get number of times you get interest. So it's the same calculation as before, which is number of years times the compounding period. So that will work here as well. Okay, so let's just verify that if we use this formula, we get the same answer as the table. So if I know that A is what I'm looking for, the future value or the accumulated amount, R is his regular payment, I is the percent interest rate, 2.5%, written as a decimal, it's 0.025. So I is going to be this decimal divided by the compounding period, which is monthly, so it's 12. And it's going to be 12, and is the number of times you get interest. Well, if it's compounded monthly, it'll be 12 times in that year. 12 times 1 is 12. Putting all that information into the formula. And yes, you can reduce this to a decimal. You just want to try to keep at least 4 numbers that are non-zero so that you can at least get some form of an accurate answer. And then you calculate it and you get exactly what we got using the table. So after a year, he accumulated $2,427.69. And so that is the end of lesson 6. Tomorrow we'll do the follow-up. Please try at least some of these questions before tomorrow.
Bye.